Hello and welcome back to Probability and Statistics. In this video, we'll discuss conditional probability independence based theorem. So our learning goals is to know the definitions of conditional probability and independence of events, be able to compute conditional probability directly from its definition, be able to use the multiplication rule to compute the total probability of an event, be able to check if two events are independent, be able to use Bayes' formula to invert conditional probabilities, be able to organize the computation of conditional probabilities using trees and tables, and understand the Bayes rate fallacy. So we'll start off with conditional probability. So conditional probability answers the question, how does the probability of an event change if we have an extra information? So we'll illustrate that with an example. So let's say, for instance, what is the probability of 3 heads? So we have the sample space here. We have a total of 8 outcomes. So all outcomes are equally likely. So the probability of 3 heads is equals to 1 over 8. Since we only have one outcome which has 3 heads. Okay, so this one. So the first one. So that means that the probability of 3 heads is equals to 1 over 8. So another is, suppose we are told that the first toss was heads. Given this information, how should we compute the probability of 3 heads? So we have a new reduced sample space now. So the original sample space consists of 8 outcomes, but here we have a condition that the first toss was heads. Okay, so that means we'll only get the outcomes which the first toss is heads. So here we have this one. So the first, the second, the third, and the fourth. So the rest will remove that. And we have now the reduced sample space, which consists of 4 outcomes. So in the reduced sample space, all outcomes are equally likely. So the probability of 3 heads, given that the first toss is heads, is 1 over 4. Now, it becomes 1 over 4 because of the reduced sample space. We only have 4 outcomes. So that means the probability of 3 heads, given that the first toss is heads, is only 1 over 4. Okay, so that's how conditional probability works. So conditional probability in formal definition is rephrased, let A be the event all 3 tosses are heads. So, and let B the event the first toss is heads. So the conditional probability of A knowing that B occurred is written as the probability of A given B. Okay, so this read as the conditional probability of A given B, or the probability of A conditioned on B. So simply the probability of A given B. So we'll call this as probability of A given B as a short term. So we can visualize conditional probability as follows. So think of the probability of A as the proportion of the area of the whole sample space taken up by A. For A given B, for the probability of A given B, we restrict our attention to B. So that is probability of A given B is the proportion of the area taken up by A. So this one. So here, as you can see, the abstract visualization of the coin example. So we have here the outcomes, the sample space. So if we condition that the first toss is heads, we only have now 4 outcomes. And then so from 8 it becomes 4. So the sample space was reduced. So the probability of 3 heads, given that the first toss is heads, it will become 1 over 4. Okay, so it is also represented in Venn diagram here. So let's come now to the formal definition of conditional probability. So let A and B be the events. So we will define the conditional probability of A given B as the probability of A given B is equals to the probability of A intersecting B, or the probability of A intersection B over the probability of B, provided that the probability of B is not equal to 0. So there is a condition that the probability of B is not equal to 0. So that means the probability of B should be greater than 0. So let's say for instance, here we have the A is 3 heads and the condition is, or the B is, the first toss is heads. So the probability of A is 1 over 8. The probability of B is 1/2, since we only get the first toss is heads. So from 8 it becomes 4, so it becomes 1/2. So the intersection of A and B is equals to A. So that means that the probability of A intersection of B is equals to 1 over 8. So if we use the conditional probability formula, 1/8 divided by 1/2 will be equal to 1/4. Okay, so that's how we compute conditional probability more formally. So here is another example. So let's say for instance we roll a die. The sample space for that is 1 until 6, 1, 2, 3, 4, 5, 6, since a die is consists of 1, 2, 3, 4, 5, 6 outcomes. So we'll consider the two events. So A, we have 1, 2, 3, 4, 5, and B is 3, 4, 5. So what is the conditional probability of A given B? So if we will going to use the formula of the conditional probability, if we get the probability of A intersecting B, that is 3 over 6. Why? Because in the event A, we have 3, 4, 5. In the event B, we also have 3, 4, 5. So we only have three outcomes. So that's 3 over 6, since we have the total sample space of 6. So here we have 3, 4, 5. In B, we also have 3 or 4, 5. Yan. So that means that the probability of A intersecting B is 3 over 6. So over the probability of B, which is 4 over 6, since in B we have 3, 4, 5, 6. So if we divide 3 over 6 with 4 over 6, we'll get 3/4. Okay, so yeah. So we come now to multiplication rule. So in multiplication rule, the following formula is called. So here we have the probability of A intersecting B is equals to the probability of A given B multiplied by the probability of B. We can also invert that. No, the probability of A intersecting B is equals to the probability of B given A multiplied by the probability of A. So if A and B are independent, this simplifies to the probability of A intersecting B is equals to probability of multiply the probability of B. So if A and B are not independent, you will use the formulas above. But if A and B are independent, you will use the formula below. Okay? So that's the formula for multiplication rule. So here is an example. So let's say for instance we will draw 2 cards from a deck. So S1 is equals to first card is a spade, and S2 is equals to second card is a spade. So what is the probability of S2 given S1? So we can do this directly by counting. If the first card is spade, then 51 cards remaining, so 12 are spades. So here we have the probability of S2 given S1 is 12 over 51. Okay, so to explain that further, diba in a card, 52 cards, a set of cards, we have 52. So there are 13 spades from ace to king. So that's 13. So ace, 2, 3, 4, 5, 6 until 10, and then jack, queen, king. So that means we have 13 cards which are spades. So in the condition here, we have S1, the first card is spade. So that means nabunot na natin yung isang card na spade. So that means we only have 12 card na spades. So in the second card, we can get the probability of 12 over 51 since nabawasan na from 52, nabawasan na nung first card na spades. So that means that's only 12 over 51. Okay? So the probability of second card is spades, given that the first card is spade, we only have the probability 12 over 51. Okay? So now let's compute this formula. Now let's recompute this example using the formula. So we have to compute the probability of S1, the probability of S2, and the probability of S1 intersecting S2. We know that the probability of S1 is 1/4 because there are 52 equally likely ways to draw the first card, and 13 of them are spades. So like what I've said, kaya siya 1/4 because if we are going to view a deck of cards, kung makikita nyo, 13 doon is spades. So 52 divided by 13, that's 1/4. So 1/4 doon is spades. So the same logic says that there are 52 equally likely ways the second card can be drawn. So the probability of S2 is equals to 1/4. So continuing, we see that the probability of S1 intersecting S2 is 13 over 52, 13 multiplied by 12 and over 52 multiplied by 51. If we compute for that, we will get 3 over 51. Okay? So the probability of S1 intersecting S2 is 3 over 51. Okay? So this was found by computing the number of ways to draw a spade, followed by a second spade, and dividing by the number of ways to draw any card followed by any other card. Now, using the formula 1, we get the probability of S2 given S1 is equals to probability of S2 intersecting S1 over probability of S1. So we have now the probability of S2 intersecting S1, we have 3 over 51, and the probability of S1, which is 1/4. So the probability of S2 given S1 will be 12 over 51, as or the same as we get in the first computation. Okay, so finally we verify the multiplication rule by computing both sides of 2. So as you can see here, the probability of S1 intersecting S2 is 3 over 51, and in multiplication rule, as you can see, if you will use the multiplication rule, we can also get 3 over 51, since the probability of S2 given S1 is 12 over 51 multiplied by 1/4, or the probability of S1, will get 3 over 51. Okay, so that's how multiplication rule works. Okay, so we come now to the law of total probability. So the law of total probability will allow us to use the multiplication rule to find probabilities in more interesting examples. So it involves a lot of notation, but the idea is fairly simple. We state that the law when the sample space is divided into 3 pieces. It is a simple matter to extend the rule when there are more than 3 pieces. So here, suppose the sample space is divided into 3 disjoint events. So we have the B1, the B2, and the B3. So later on, I will show the figure. Then for any event A, so the probability of A is equal to the probability of A intersecting B1 plus the probability of A intersecting B2 plus the probability of A intersecting B3. So the top equation says if A is divided into 3 pieces, then the probability A is the sum of the probabilities of the pieces. So in the bottom equation, so we have the probability of A is equals to the probability of A given B1 multiplied with the probability of B1 plus the probability of A given B2 multiplied by the probability of B2 plus the probability of A given B3 multiplied by the probability of B3. So the bottom equation says that it is called as the law of total probability. It is just a rewriting of the top equation using the multiplication rule. As you can see here, we are getting the multiplication, we are using the multiplication rule here, here, and here. Okay, so that's how the total probability works. So the sample space and the event A are divided into 3 disjoint pieces. So as you can see here is the figure. So the law holds if we divide sample space into any number of events so long as they are disjoint and cover all of sample spaces. Such a division is often called a partition of sample space. So our first example will be one where we already know the answer and can verify the law. So here's an example. So let's say, for instance, an urn contains 5 red balls and 2 green balls. 2 balls are drawn one after the other. So what is the probability that the second ball is red? So we are looking for the probability of R2, which is the second ball is red. So here we have the sample space RR, RG, GR, and GG. So the first outcome is RR. So the first ball is red, the second ball is red. In the second outcome, the first ball is red, the second ball is green. The third outcome, the first ball is green, the second ball is red. The fourth outcome, we have the first ball is green and the second ball is green. So we have here the event. So the event R1, the first ball is red. So the event G1, the first ball is green. The event R2, the second ball is red, and the G2 is the second ball is green. So the fastest way to compute this is just like the probability of S2 in the card example. Every ball is equally likely to be the second ball. Since 5 out of 7 balls are red, the probability of R2, which is the second ball is red, is 5/7. So let's compute the same value using the law of total probability. First, we will find the conditional probabilities. This is a simple counting exercise. So the probability of the second ball is red, given that the first ball is red, is 4/6. And the probability of the second ball is red, given that the first ball is green, is 5/6. Okay? So, since R1 and G1 partition, the law of probability says the probability of the second ball is red is equals to the probability of the R2 or the second ball is red, given that the first ball is red, multiplied by the probability of the first ball is red, plus the probability of the second ball is red, given that the first ball is green, multiplied by the probability of the first ball is green. So we have here 4/6 multiplied by 5/7 plus 5/6 multiplied by 2/7. That is equals to 3/42, which is equals to 5/7. Okay? So another example is an urn contains 5 red balls and 2 green balls. A ball is drawn. If it's green, a red ball is added to the urn. So if the first ball is green, so a red ball will be added to the urn. And if it is a red, a green ball will be also added to the urn. So that means kapag nakabunot ka ng green, so you will add red ball to the urn. Kung nakabunot ka ng red, you will add green ball to the urn. Okay? So the original ball is not returned to the urn. So yung nabunot mo or the original ball will not be returned to the urn. So then a second ball is drawn. So what is the probability the second ball is red? So the law of total probability says that the probability of the second ball is red can be computed using the expression in equation 4. Okay? Only the values for the probabilities will change. We have the probability of the second ball is red, given that the first ball is red, is now 4/7. And the probability of second ball is red, given that the first ball is green, is equals to 6/7. Therefore, the probability of red ball, the second ball is red, is equals to the probability of the second ball is red, given that the first ball is red, multiplied by the probability of the first ball is red, plus the probability of the second ball is red, given that the first ball is green, multiplied by the probability that the first ball is green, is equals now to 4/7 multiplied by 5/7 plus 6/7 multiplied by 2/7. That is 32/49. Okay? So we can also use trees to organize the computation. The trees are a great way to organize computation with conditional probability and law of total probability. So the figure and examples will make clear what we mean by a tree. As with the rule of product, the key is to organize the underlying process into a sequence of actions. So we start by redoing the example 4. So the sequence of actions are: first draw ball 1 and add the appropriate ball to the urn, and then draw ball 2. So here it's an example. So here the probability of the first ball is red is 5/7. So if the second ball is red, the probability is 4/7. But if the second ball is green, the probability will be 3/7. Since we are adding green green ball if we draw a red ball. So here nakabunot tayo ng red. So that means magdadagdag tayo ng isang ball na green. So kaya naging 3/7 yung green ball. And then kukunin natin yung isang red ball, kaya naging 4/7 na lang. So that's the idea. On the other hand, so we have, if the first ball is green, the probability is 2/7. And then if we are going to follow the rule that yung nabunot natin is green, so magdadagdag tayo ng isang red. So that means from 5/7 plus 1, magiging 6/7 yung red natin. As well as yung green, mababawasan ng isa, from 2/7 magiging 1/7. So that's how you interpret or compute the probability using threes. Okay? So organizing the computation using threes. Okay? So shorthand versus the precise tree, this is an example. So here we have the probability of R1 is equals to 5/7, like what I've said earlier. So if we draw red, so we'll add 1 to the green and we will minus 1 to the red. Okay, same with the green. The first pick is green, so that's 2/7. The probability of the first ball is green is 2/7, but we'll add a ball to the red. Since we draw green, we add 1 to the red, so that's 6/7. The probability of the second ball is red, given that the first ball is green, is 6/7 now. And then we'll minus 1 to the green ball, since the probability of second ball is green, given that the first ball is green, is equals to 1/7. So that's how you represent in shorthand and versus the precise. Okay, tree. So this is an example of a precise tree. So we come now to the independence. So two events are independent if knowledge that one occurred does not change. The probability that the other occurred informally. Events are independent if they do not influence one another. Okay, so here is an example. So let's say, for instance, we toss a coin twice. So we expect the outcomes of the two tosses to be independent of one another. So in real experiment, this waste has to be checked. If my coin lands in honey and I don't bother to clean it, then the second toss might affected by the outcome of the first toss. Okay. So in formal definition, events A and B are independent if and only if the probability of A intersecting B is equal to the probability of A multiplied by the probability of B. So here we prove that, no? So by using the formula of conditional by using the formula, so as you can see, this formula, so the probability of A given B is equal to the probability of A multiplied by the probability over the probability of B. We cancel out this, or we simplify the equation, so cancel probability of B and the probability of B. So we only have now the probability of A given B is equals now to probability of A. Same with the invert. So probability of B given A is equals to probability of A multiplied by the probability over the probability of A. Cancel the probability of A, probability of A. We only now have probability of B. But there's a condition that for probability of B should be greater than 0 and the probability of A should be also greater than 0. Okay? So that's how independence works. So we'll give you an example here. So let's say for instance, we toss a fair coin twice. So the event H1 is equals to heads on first toss and H2, which is equals to heads on second toss. So are H1 and H2 independent? So the answer for this would be, since H1 intersecting H2 is the event both tosses are heads, we have the probability of H1 intersecting H2 is equals to 1/4. Okay? So the probability of H1 intersecting H2 is equals to probability of H1 multiplied by the probability of H2, which is equal to 1/2 multiplied by 1/2 is equals to 1/4. Okay? So that means that is independence. So here is another example. We toss a fair coin 3 times. So the H1 is heads on the first toss and A is 2 heads in total. So our H1 and A are independent. So the probability of A, we all know that it's 3/8. Since we have 2 heads, we have 3 outcomes, or 2 heads in total over 8 outcomes. So we have here the H1, we have 4, the first toss is heads. So we have, in the previous example, that's 1/4 or 1/8 in sample space, but in reduced sample space, that's 1/4. So it contains exactly 2 outcomes. In the reduced sample space here, the H1, it contains only exactly 2 outcomes with 2 heads in totals, this one and this one, the second and the third. Okay, this one, the second and the third. So the probability of A given H1 will be this one, so 2/4 with the reduced sample space of H1. So the probability of A given H1 is not equal to probability of A. So then these events are not independent, since the conditional probability is not equal to the probability of A. Okay? Yeah. So that's how you interpret independence. So another example, draw 1 card from a standard deck of playing cards. Let's examine the independence of 3 events. The card is an ace, the card is a heart, and the cards is a red. So we'll state an event A, which correspond to ace, H for hearts, and R for red. So here for A, the probability of A is 4/52, since we only have 4 aces over a standard deck of cards, which is 52. That is, if we simplify, that is 1/13. So we also have probability of A given H. The probability of aces given the condition that the cards is hearts is 1/13. Since we have a condition that the cards is hearts, so we have, in a standard deck of card, we have 13 cards, total hearts, 13 total cards of hearts, and then we only, in that condition, which is only hearts, we have only 1 ace. So that means that the conditional probability is 1/13. So the probability of A is equals to the probability of A given H. So we have that A is independent of H, since the probability of A is equals to the probability of A given H. Okay? So for B, the probability of A given R is equals to 2/26. Why? The probability of aces in red is only 2. Since in a standard deck of cards, we only have 26, I think 26 red cards. The diamonds and the hearts. So that means that we only have 2 aces in a red cards. Okay, so that's 2/26. Yeah. So which is equals to 1 also. If we simplify that, we get 1/13. Okay, so in C, the probability of H is equals to 1 over 4, and probability of H given R is 1/2. H and R are not independent. So hearts and red are not independent, since P of H is not equal to the P probability of H given R. Same with the probability of red is equals to 1/2. Why 1/2? Because half of the cards is red. We have the diamonds and the hearts, which is 26 over 52. So that's 1/2. And the probability of red given hearts is equals to 1. Okay, so H and R are not independent, since P of reds is 1/2 and the P of R given H is 1. Okay, so the paradoxes of independence. An event A with probability 0 is independent of itself, since in this case both sides of the equation 6 are 0. So this appears paradoxical because knowledge that A occurred certainly gives information about whether A occurred. We resolve the paradox by noting that since probability of A is equals to 0, the statement A occurred is vacuous or empty. Okay? So that's the paradox of independence. We come now to Bayes' theorem. Okay, Bayes' theorem is a pillar of both probability and statistics, and it is central to the rest of this course. Okay. So here's the formal definition of Bayes' theorem. For two events, A and B, Bayes' theorem, also called as Bayes' rule and Bayes' formula, says that the probability of B given A is equals to the probability of A given B multiplied by the probability of B over the probability of A. Bayes' rules tells us how to invert conditional probabilities. Example, to find the probability of B given A from the probability of A given B. So in practice, probability of A is often computed using the law of total probability. So the proof of Bayes' rule, so the key point is that A intersecting B is symmetric in A and B. So the multiplication rule says that the probability of B given A multiplied by the probability of A is equals to the probability of A intersecting B, which is also equals to the probability of A given B multiplied by the probability of B. Now divide through by P of A to get the Bayes' rule. A common mistake is to confuse the probability of A given B and the probability of B given A. They are different. Okay, they are different. These two are different. The probability of A given B and probability of B given A. This is illustrated in the next example here. So toss a coin 5 times. So let H1 be the first toss is heads, and HA, all 5 tosses are heads. Then the probability of H1 given HA is equals to 1, but the probability of HA given H1 is 1 over 16. So for practice, let's use the Bayes' theorem to compute the probability of H1 given HA using probability of HA given H1. So the terms are the probability of HA given H1 is equals to 1 over 16, and the probability of H1 is equals to 1/2. So the probability of HA is equals to 1 over 32. So the probability of H1 given HA is equals to the probability of HA given H1 multiplied by probability of H1 divided by the probability of HA, which is equals to 1 over 16 multiplied by 1/2 over 1 over 32, which is equals to 1. So that means it agrees with our previous calculation here that the probability of H1 given HA is 1. Okay? So that's how Bayes' theorem works. So the Bayes rate fallacy. So the Bayes rate fallacy is one of the many examples showing that it's easy to confuse the meaning of the probability of B given A and the probability of A given B when a situation is described in words. So this is one of the key examples from the probability, and it will inform much of our practice and interpretation of statistics. You should strive to understand it thoroughly. So the Bayes rate fallacy, so Consider a routine screening test for a disease. Suppose the frequency of the disease is in the population, or the base rate is 0.5%. The test is highly accurate with a 5% false positive rate and a 30% false negative rate. You take the test and it comes back positive. What is the probability that you have the disease? So the answer for that is, we'll do the computation 3 times using 3 tables and symbols, but I will only discuss it using the symbols. We'll use the following notation for relevant events. So D plus is equals to you have the disease, D minus you don't have the disease, T plus you tested positive, and T minus you tested negative. So here we are given the probability that you have the disease is equals to 0.005, and therefore the probability of that you don't have the disease is equals to 0.995. So the false positive and the false negative rates are by definition the conditional probability. So the probability of false positive is also denoted as the probability of you've tested positive given that you don't have the disease is equals to 0.05, and the probability of false negative, which is the probability of that you tested negative and given that you don't have the you have the disease is equals to 0.1. So the complementary probabilities are known as the true negative and true positive rates. So here is the probability of you've tested negative given that you've tested you don't have the disease is equals to 1 minus the probability of that you've tested positive given that you don't have the disease is equals to 0.95. We minus 1 minus this one, so that means we have 0.95, and the probability that we've tested positive given that you have the disease is equals to 1 minus the probability of you've tested negative given that you have the disease is equals to 0.9. Since we are 1 minus this one, so 1 minus 0.1 is 0.9. Okay, so we are only getting the complementary probabilities. So all of these probabilities can be displayed quite nicely in a 3. So here is an example. If you don't have the disease, the probability is 0.995, and you've tested positive, that's 0.5, and if you've tested negative, that's 0.95. If you have the disease, the probability is 0.005. If you tested positive, that's 0.9, the probability is 0.9, and if you tested negative, that is 0.1. Okay, so the question asks for the probability that you have the disease given that you've tested positive. Example, what is the value of probability of you tested positive in the disease given that you've tested positive? We aren't given this value, but we don't know. We do know the probability of you tested positive given that you have the disease, so we can use the Bayes theorem here. So the probability that you have the disease given that you've tested positive is equals to the probability that you've tested positive given that you have the disease multiplied by the probability that you have the disease over the probability that you've tested positive. So here, the two probabilities in the numerator are given. So we compute the denominator of the probability of T, the probability of that you have tested positive using the law of total probability. So using the 3, we just have to sum the probabilities for each of the nodes marked that you have tested positive. Okay, so the probability that you tested positive is equals to 0.995 multiplied by 0.05 plus 0.005 multiplied by 0.9 is equals to 0.052425. So thus, if we'll use the Bayes theorem formula, the probability that you've positive, yeah, that you have the disease, given that you've tested positive, is equals to 0.9 multiplied by 0.005 over 0.05425, which is equals to 0.082949, which is approximately 8.3%. So this is called the base rate fallacy, because the base rate of the disease in the population is so low that the vast majority of the people taking the test are healthy, and even with an accurate test, most of the positive will be healthy people. So ask the doctor for his or her guess at the end. So to summarize, the base rate fallacy with specific numbers, so 95% of all tests are accurate, does not imply that the 95% of positive tests are accurate. Okay? So here is the visualization. So as you can see, so the figure below illustrates that the base rate fallacy. So the large blue area represents that all the healthy people. So we have the population, we have a larger population that the people doesn't have the disease. Look at this one against the population that has the disease. So that's the base rate policy. Okay, so as you can see here, the intersection, so mas madami pa rin yung tinest na konti kaysa sa, or I mean, mas madami pa rin yung mga taong tinest ng walang disease kaysa sa taong mga tinest na may disease. Okay? So that's the base rate fallacy. So that's it for conditional probability and independence and Bayes theorem. So if you have any questions, you can raise it on our group chat. So thank you for listening and see you next week. Thank you.